Our next speaker is Michael Andrews, exploring end-to-end deep learning, CMS.
Okay, so I'll give you guys a talk about what we're trying to explore. So this is, at this point, a largely exploratory project. So what we try to do is what's called end-to-end deep learning for event classification. So before going into that, I sort of explain, a caricature of how event classification is typically employed at physics analyses. So typically, at the very low level, your detector data exists as sensor data. So it's just so at this point, just take it for a cartoon. But from this low-level detector data, this will slowly get through the physics reconstruction process. Will slowly be forced into a representation of physics variables, of essentially hand-engineered features. So I should mention that what we consider high-level is what many people in the talks here have still considered as low-level. So by low-level, I really mean the stuff, the deposits in your detector. Okay, and so it's usually this which comes as the starting point for whenever you try to do event classification. Okay, so physics data going to a class prediction. So the end-to-end approach, in contrast, would be to start from the detector data and immediately output a class. So the motivation is perhaps the physics reconstruction process is a lossy process. So this is the idea we would like to play with. I'm not saying it's in fact the case, but it's the idea we're playing with and what we think is worth investigating. So the natural way to exploit sensor data in this fashion is to use convolutional neural nets. So this is what we use. Okay. So we're doing this with the CMS detector, and though you've seen this many times, I should mention that CMS detector works by using different subdetectors to piece together different particles. So in particular, when we start this project, we want to look at just the electromagnetic calorimeter, which is this green stuff here. So this is the ECAL, and its job is to record the energy deposits of either photons or electrons. Okay. So we only look in ECAL. The ECAL by design is supposed to be insensitive to showers induced by photons or electrons. So in practice, the discrimination between photons or electrons is provided by the information from the track here. Okay? So both from a hardware perspective and also from a software perspective, ECAL and E-gamma reconstruction are designed so that we are insensitive to the differences between photons and electron showers in ECAL. Okay? So this is a picture of the ECAL barrel section in green. Just to acquaint you with ECAL a little more, this is a longitudinal section of the ECAL subdetector. And so each of these bands here is actually a crystal, and you can see that they tilt inwards. So this is the barrel section, and this is the end cap section. Okay. And so the natural way to turn this into an image is to just unroll the barrel. So we restrict ourselves to the barrel first. And so the natural way to do this is to just unroll the barrel. And we use the natural segmentation of ECAL, which is I phi, and I eta. Okay? So this image here is an image of the actual deposits to the ECAL detector. So this is not a pixelated image that we use for high-level objects. It is the lowest level detector deposits into the energy deposits into the ECAL crystals. Okay, so a little more about ECAL. So how do we do hit reconstruction in ECAL? So all these crystals use what are called scintillating crystals. So a particle comes in and induces a shower, as illustrated here. Okay, now the shower will create a signal pulse that is recorded by the electronics. Okay, so you get this sort of pulse shape. Now, due to data acquisition constraints, we can only sample this pulse 10 times. So you see these red dots here, they're all spaced between 25 nanoseconds. So if the trigger says that we should trigger on an event, we read out the amplitude of the crystals 10 times in an event. So these amplitudes are in ABC counts. Okay, so technically speaking, raw data for eCal is ones and zeros. When you unpack the raw data, what you get are these digitized hits. So for each crystal, you get a pulse shape, and if you sort of form a 32 by 32 grid of crystals, what you get is actually a short video of the evolution of the shower in the crystal. So this is an ABC counts. Okay? Now, after these ABC counts, based on the shape, based on the height of the pulse, and the shape of the pulse with respect to a reference pulse shape, one infers the energy and the timing of the hit. So there are other quantities that are stored in the rec hit collection, but these are the two most important ones for our purposes today. Okay, and so this is typically called the reconstructed hit or the rec hit. So the rec hit is the lowest detector level collection that is calibrated. Okay, so the digis are a short video, and the rec hits are basically a converted snapshots of the hit. And so I should cite many similar work that's been done in this area. So of course the neutrino experiments have done extensive work on convolutional nets. So there's been many jet image work that's been involved. So you can see these workshops on Ben's talk from yesterday. So there's also been use for event classification, not using images, but using a natural language processing approach. And there's also been some use within eCal of looking at supercluster records. So this may not make much sense. But I should also point out a talk yesterday by Wahid, who also did something similar to what we did. We used full detector images. So I should note that in contrast to other image approaches, we actually use the low-level detector hits. We do not pixelate. We just read out what comes from the crystal deposits. So although we would like to do event classification as sort of baseline and sort of to get our feet wet into this project, we started with object classification. Okay? And so what we tried to discriminate against, what was the easiest to implement, is to just distinguish electrons or photons in eCal. So for this, we used a sample of fixed PT, 50 GeV, eta less than 1.4, which just makes sure it only hits the barrel. No pileup or underlying event, and as an added reminder, eCal is not designed to distinguish between photon and electron showers. So if ever we find anything, we're picking up a very high order subtle effect. Okay? So for this, we actually take a 32 by 32 grid of crystals centered on the shower seat. So this is illustrated as such. So we start with the image of the barrel, and then we center on the seat and take a 32 by 32 set of crystals, and voila, you get this picture. And we want to classify it as either photon or electron, if possible. Okay. So why 32 by 32? So there's a physics reason for this, and there's also a machine learning reason for this. So the machine learning is that when we started this, we had no idea if this would ever work. So we wanted to use an image input that had been well understood. And so if you learned about convolutionals, you know that many of these MNIST data sets are close to 32 by 32. And so in this manner, we eliminated the risk of using a network that we weren't sure could work. Okay, so we knew that if this did not work, it was something to do with the inputs. Okay. So this is a picture of an average photon shower at 50 GeV, and this is a picture of an average electron shower. So this is over about 50,000 events. So as you can see, it's very hard to tell them apart. Okay. So what I will point out some subtleties here. So one thing you'll notice is the electron shower is slightly more spread out. Okay. Now, this is probably not the best visualization, but the center of the electron is also slightly weaker. And what's happening here is that the electron, because it interacts with the magnetic field, because it turns, it emits a little bremsstrahlung, and because it's also interacting with the tracker acts as a very weak pre-shower to sort of distribute the shower somewhat. And there's another effect which is hard to see. I don't know if you'll see it from here. But if you look at this second pixel from the center, it's actually not balanced with the one on the left. Okay, so in fact, the electron shower is actually asymmetric. And this is because the electron also bends in the track and enters at an angle. And so if you go back to the illustration of the CMS detector, you'll actually see that this is implemented in the illustration. So this is the photon, which is shooting straight, and this is the electron, which is actually bending a bit at an angle. So it's a very subtle effect, and I would say that this is exaggerated. In any case, so we start with a baseline architecture, which is the VGG, which is essentially just some stack convolutions followed by max proof. And so the figure of merit, so I let you guys read this on your own. So the main figure of merit we have for now is the rock AUC, or the area under the curve of the receiver operating characteristics. So I won't go into too much detail about object classification, but I'll tell you a little about the things we tried. Okay, so we tried different ways of pre-processing. So we tried just linear rescaling, log rescaling, and pedestal subtraction in the case of the digis and the record collection. So it's a bit of a long story. Other than the pre-processing, we also tried 3 different architectures. The convolutional neural nets, and in the convolutional neural nets, we tried VGG, inception, and residual nets. And for the object classification, we can tell you that there was little to no difference to using the VGG to the other more fancy architectures for object classification. But I will get back to this later on. And so we also tried a fully connected network where we flatten out the images, and we tried different fully connected networks just to see if the score is constrained by the inputs or the capacity of the network. So in this case, the 3-layer actually worked better than the 6. And in addition, because the digis, if you recall, are a sequence of images, essentially a short video of the shower evolution, we also tried applying LSTMs in 2 implementations. The time-distributed CNN is where the digis, you have 10 of them. Instead of stacking them all in one convolutional net, you actually have 10 distinct convolutional nets which feed into, which you flatten, then go to an LSTM. So that's the first one. The second one is where the LSTMs will actually operate on the convolutional layers themselves. In addition, we also tried different combinations of inputs. So we tried just the energy reading from the record, the energy and the time, the digi, the energy, time, and the digi. And for this final one here, we also experimented with different ways of how you concatenate the inputs. So you can either concatenate them at the input level, or at the output of the convolutional layer, or at the output of the fully connected layer. And so we only report here the best for each architecture. So the best we got is using the convolutional neural net using just the energy inputs. So the fully connected, as expected, did not do so well. The LSTM didn't do so bad, but there are other reasons why you don't want to go with digis. For one, they're a lot longer to train because you have 10 layers instead, plus the LSTMs take a lot longer to train. Second is the digis. From a physics perspective, the digis are actually uncalibrated. And so what happens is you're actually exposed to transparency losses with the ECAL crystals. So the ECAL crystals, as they get bombarded by radiation during the fills, their transparency actually changes. Okay, so this is what the laser calibration in ECAL is for, and so these are corrected offline. So once you get to the rec hit energies, these are already corrected for, but these do not exist at the digi level. So even though they get close, when it comes to comparing to data, you're likely to encounter problems here. So this is good for us because the simplest approach seems to work the best. Okay. So now the real meat is event classification. So the main issues you want to address in event classification is scale. So you've had an image where the shower is always at the center of the image. But now you're using a full detector image where the shower is now bouncing around the image. Okay? And second is, can we somehow exploit the correlations between different objects in the image to surpass our single object score? Okay? And as a primer here, I should note that once we switch to the full images, so the ECAL barrel images are 170 by 360. So the VGG did not very good once we started here. So the VGG, because it has this So the VGGs in general suffer from what's called this degradation problem. And so what this is that for deeper networks, your training loss starts to go down. So this is not an overfitting issue, which arises in the validation loss. This is an actual lower training score. And so the other thing is the VGG uses a fully connected layer. And if you're using a big image, the number of weights will weakly scale with the size of your image. Okay? So this is where the residual net started to work very beautifully. So the VGGs were very difficult to train because of the ballooning of the weights. But the the residual nets work very beautifully here. So you get away from the degradation by using these so-called identity shortcuts, and the fully connected explosion, you get rid of it by using a global max pool. Okay, and so this is an example of a typical image. And so the score we get is 0.788, which you'd want to compare to 0.807. So it's not a huge hit, but from this study, it's hard to make a case for event classification when just looking at the single shower will work best, right? So where things really get interesting is when you have more than two objects in the image. So now I'm looking at an E plus and E minus versus two photons. Now I'm also using a range of PT values, still shooting in the barrel, and now these particles decay back to back. I also throw in some pileup here to make things interesting. And so you can see a typical image here. Okay. Now suddenly, once we do this, the score drastically gets a boost. So we're up at 0.997 all of a sudden, once there's two objects in the picture. So what's going on here? So we were a bit surprised by this result, but if you think about how correlation works, what does it mean to exploit the correlation between two objects? If you know that one shower has a miss ID rate of 25%, then the probability that you will miss ID both of them at the same time is now 25% times 25%, which is 6%. So if your classifier knows that they're correlated and is able to exploit this correlation, then this result is something you expect. Okay? And this is what we've demonstrated. Without explicitly telling the classifier how the showers are correlated, this was learned on its own. Okay?
Sorry. That's just squaring. There's no correlation in your example. Just two things. Assume that
I didn't do that.
You said 25% time.
Is
It's definitely true that the two different things.
So can you let me finish? We can discuss this after. So this is all I can show you for now, since we have to go through approval. Because this is a detector level image, we actually have to get approval from ECAT, from E-gamma reconstruction. And if you want to show you physics, we have to get approval from the physics group as well, which we don't have, so we can't really show you. But I will tell you a bit about what we're doing. So we have begun in earnest looking at realistic proton-proton physics processes. So we've also shown that we can not just exploit correlations in the substructure of the shower, but we can also correlate correlations in the spatial distribution of the same shower. So we had also tried to shoot two photons, one in which the distribution between the two photons was random, and another they were correlated. And so this is also able to tell them apart. We also did studies to try to train on samples of different PT regimes, where you train on one PT regime and then on another and ask this model to evaluate on the test set of another PT regime. And we also got good results for this. We also trained on not just the barrel, but also the end caps. We haven't gone to data validation yet. So in principle, there's more, doing a physics analysis is more than just raw event classifier performance. There's other concerns. For instance, and this is true of any event classifier, the background events that are misclassified as signal tend to look like your signal. So depending on the physics observable you're looking at, you can be led into thinking you actually had signal from the events that pass your background. And so you have to find, so the real trick is in finding a way to achieve both the physics results without impacting your classifier performance too greatly. And so what we showed is that the most sensible low-level thing to use is Redkit's convolutional nets on low-level detectors show good performance in single objects, and once more than one object is involved, it seems to be very good at exploiting correlations. So beyond the physics, we're also trying to see if we can combine information from the distant detectors in a way that is faithful to the granularity of the detectors. And that's all. I think I had a question.
Sorry, I didn't mean to interrupt. I didn't know if the questions were for or after. I think using the correlate, there's two pieces of information, so you have two handles, but actually you're going to get more information. I wouldn't necessarily call that any kind of correlation. If you, for instance, knew that they came in E plus E minus pairs and not E plus E plus pairs and minus E minus, or some kind of weird, if this thing scattered that thing, that's something weird. So it's just two electrons versus two photons. It's just like a thing.
Oh, but that's because you're assuming it's not a photon, electron, photon.
But I'm just saying that's baked into the.
So I should say that this is a work in progress. This was the goal here is really to understand how you can feasibly do event classification. So of course, if you had a photon and electron, then you would be constrained again by your single object classification. So the idea is to progressively include information from other subdetectors. And as a starting point, we started with one detail.
Yeah, I mean, I think it's a nice approach to use the level objects, but I think kind of in the same vein, I would argue that your performance on a given event classification is basically factorized. Like your ability to identify a photon is independent of your ability to identify two photons is sort of the product of the ability to identify two photons. So it doesn't. There's no global event structure that you built an optimal photon classifier and use both of those and optimally combined to figure out what kind of event it is. I think it couldn't do any better. It's like a similar thing for your energy reconstruction, right? As you showed, that the energy is actually sufficient statistic for the whole energy curve. And once you know the energy, there's nothing more to learn.
So the correlation in the shower shapes is only one part of the equation. The other part of the equation is exploiting the correlations in the spatial distribution. So I haven't showed it here and I can't show it here. But the other piece of the puzzle is what if you have two photons? In one way, the photon positions are correlated and the other, they're shot randomly. So we also showed that we were able to get good discrimination on this kinds of study.
I think it's super interesting. To me, it's a weird question. If you have a situation where you have like electron versus photon, say, and your signal at the event level, has some different kinematics.
So
then the question is, do you want to take it? Do you want the photon piece to be independent?
So okay, I should say that the electron versus photon. This is just a technical demonstration.
Sure, no, I don't mean
We're not suggesting that we would actually implement an electron to photon classifier.
And I meant philosophically, it's kind of weird because usually the field the way we've operated is build object ID, and then we usually try to have relatively flat performance across PT and various things that these characterize, and then we apply it to some physics where the kinematic structure gets laid on top, right? When you put it into when you do end-to-end learning, you don't necessarily get that. You get something that's like optimized over the signal characteristics at the level that you want. It's not criticism. It's just this thing, right? That for the field, it's kind of an uncomfortable place to go. Like, do we want that property? Do we not want that property? We're not very used to thinking about it. And like the little bit of work that we did a lot of work to try to kind of decouple those two, or to try to understand how much we got, how much additional performance we got that really had to do with kinematics and not to do with object ID and stuff. It's not a criticism. I just
yeah. I mean, certainly, it's an unorthodox approach, and it's quite a controversial because we sort of have to let go of the wheel when the classifier makes a decision. So the idea is not to completely divorce from reconstruction. So there is still the reconstruction path, which will provide you information about the PT of the photon if you decide to investigate it in detail. But for the purpose of classifying the event, the whole physics reconstruction chain is unnecessary.
Maybe I think what's nice about factorization might be the number of data you need, right? For a factorized problem, you can train that, and you might have enough data to do that well, or you do the whole reconstruction at once, put it in process. But you estimated like tracking everything, you might need billions of simulated events.
So we trained on 100,000, hundreds of thousands, and we've gone as low as 24,000, and we still lost just 1 to 2% performance.
But you also didn't went the full thing on the whatever.
I think those are questions to be.
It's a work in progress.
I think those kind of questions.
Yes.
So I've got a sort of orthogonal question, which is from a computer science point of view. It looks like you actually did something very nice, that you tried many different types of ways of organizing the data and different types of neural networks and different structures. And you drew a conclusion at one point saying the simplest was the best, or something like that. But from a computer science perspective, is there a way to identify which ones should work well? And you draw, I mean, so the next time someone starts a similar project, they have to go through all the work that you did ab initio, from the beginning, right? Or can they say, oh, they understand that this features are what are important for training neural networks, and therefore, instead of trying 4 times 4 times 4 times 4 possibilities, we can get down to 2 times 2 times 1 times 1.
So, okay, I can comment on the timing. So the timing information is, in fact, 2 cores to be able to discriminate an electron from a photon eco. So the timing
I'm not talking about this physics. I'm talking about what did you learn about different types of neural networks and how to organize the data?
So for object classification, it seems that there's just not enough variation in the inputs to make a difference between different kinds of architectures for object classification, but the story is different for event classification. So again, I can't show it here, but the one where we did 2 photons, one correlated, the other not, the effective depth had a much bigger role. So going to a deeper network gave us a few % more improvements, even more than training with more data. I don't know if that answers your question.
That helps, but the question is, can you sit down and think about why your neural networks performed the way they did, so that other people can build on your experience and not have to try as many possibilities?
So in the conclusion of residual networks.
I would like to see these things
You mean the
quantified.
digitized hit?
And then someone else would do the same type of experiment with a different question, but can we as a field build up some understanding?
Can I say that? So we had a big workshop, and it realized like half the people were machine learning.
Right, you were there.
And
they
3 of the talks were all about like, this quest to try to understand some theories. It's like a cutting edge question.
Yeah. Well,
Yeah, so the answer, I think the short answer is no. We're building up, intuition and experience.
Okay. That's what I'm wondering where we are.
Yeah.
All right, so maybe we'll just stop here for the coffee break. Let's thank Mike again.